Hey folks, welcome to another day of chemistry. Today we're going to finish up talking a little bit more about Lewis dot structures, and then we're going to move into talking about something called polarity. As you can see, I've fully just embraced distance learning. We'll see you at some point in time. Here we go. Okay, so I wanted to start off with some hints for drawing Lewis dot structures, just because, there's really only two rules, but there definitely are a lot of different things that can be considered best practices. So you might find that you have something like this already in your notes. If not, feel free to write this down. The first rule that I have here, or the first hint, I guess I could say, is that if carbon is in a compound, it goes in the middle. This is because carbon's structure is 1C and then it has 4 dots. That means it's going to form 4 bonds to get to a total of 8 valence electrons. So since it's one of the compounds that can form the most bonds, we'll always put that in the middle. Another very similar hint on a similar line is that elements with 1 valence electron or 7 valence electron, they will always go on the outside. And the reason for that is hydrogen and the halogens, the things with 7 valence electrons, hydrogen has 1. Those are the type of atoms that only form 1 bond. So if they go in the middle and they can only form 1 bond, they're not going to be able to connect if you have, 3 or 4 different atoms. So those two rules kind of go together. These are always rules. These are rules that are always true. This third rule is a sometimes rule, a rule that is sometimes true, and it's more of a hint. And that's that the center atom is usually the first atom listed. This is true with things like SO3. It's true with NO3. It's true with CH4. It's true with NH4, NH3, a bunch of different compounds that have that one unique center atom that's the first letter. It's not true with things like H2O and some others. I can't really think of any right now. So just so you know, yeah, oftentimes the center atom will be the first atom listed. So might be a good idea to write these 3 down just so you have them in your notes. Okay, we got 2 more practice problems. One of them follows that center atom rule and the other one doesn't follow that center atom rule. So go ahead and take some time to try them out. Great, let's talk about them. Okay, so nitrogen over here, let me get my pen ready. Nitrogen has 5 valence electrons, and then each of these chlorines has 7. So that means that since we have 3 chlorines, we're dealing with a total of 7 plus 7 plus 7, which means we're going to have a total of 21 dots from our 3 chlorines. That's a lot of dots to keep track of. So remember, the first rule that you do when drawing Lewis dot structures is you draw your center atom. In this case, it's nitrogen, so I'm just going to draw nitrogen here. Then, since chlorine is a halogen, right, it's going to go on the outside. Here's one chlorine. Here's another. And then lastly, here's our third chlorine. Well, bam. There it is. Okay, so now I've drawn all of my dots. You'll notice that I have a total of 21 dots from each of my chlorines and then 5 dots from my nitrogen. So my total 26 dots, that's taken care of. Now remember, the first rule is total number of electrons can't change. And the second rule is each atom needs to have 8 valence electrons. So that means we need to form bonds. Here's one bond. Here's a second bond. Here's a third. Everything's now connected. Let's just go ahead and double check. Does chlorine have 8? It's got 2, 4, 6, and 8, so yes. Does nitrogen have 8? Yes, it's got 2, 4, 6, 8. So remember, these bonds count as 2 electrons, and these pairs of dots also count as 2s. So it's always a good idea to put your electrons in pairs. In fact, you will be required to do that. So here's a little bit more clean look at what it should look like. And then for H2O, each H has 1 plus 1, so that's a total of 2. And then oxygen, 2. And then oxygen has 6 valence electrons, so the total number of electrons we're working with here is 8. So when all is said and done, we should have 8 valence electrons total. Okay, here's hydrogen, and here's another hydrogen. I'm going to put those guys on the outside, of course, because they can never go in the middle, which means oxygen then has to go in the middle. Here it is with its 6 valence electrons. Beautiful. Oxygen has 6, each hydrogen has 1. Hydrogens want 2, so we're going to form a bond here. And right away, that hydrogen has 2, so we're good. Same thing with the other hydrogen. We form a bond here, and again, it's going to have 2. Looking at the oxygen, it's got 4 dots and 2 bonds, so that's 2, 4, 6, 8. It's got 8 valence electrons. It's happy as well. Here's a little look at what it should look like a little bit cleaner. Great. So hopefully now you feel comfortable with single bonding valent Lewis dot structures. As we move forward, we're going to get a little bit more complicated with double bonds and triple bonds. So the 2 rules, though, that will always be true for all of this stuff is number 1, like I was saying before, all atoms have to have 8 valence electrons, right? So that's where you form the bonds to make sure everything's got 8. And then, of course, remember, that's 2 valence electrons for hydrogen. The second fundamental rule, then, is that the total number of valence electrons must stay the same. So in the example of NCl3, total number of electrons was 26. And in the example of water, H2O, total number of electrons was 8. In both of those cases, I didn't add any extra dots. I didn't take away any extra dots. So you'll notice just by first drawing the dots on every single atom, that's an easy way to make sure that your total number of valence electrons always stay the same. Great. So here I'm just going to show you the example P, Br, H2. This is what its final Lewis dot structure looks like. So you'll notice that your Br has 8 valence electrons. Each hydrogen has 2 valence electrons. And the nitrogen also has 8. Again, 2 dots and then 3 bonds gets it to 8 there. Another way of looking at this is looking at the total number of valence electrons. So there we go. Everything has 8 or 2 that it needs. Looking at the total number of valence electrons, there it is. You can see that I've counted up all 18, and you can kind of see, or sorry, all 14, and you can see where all 14 of those come from. Great, so both of those rules are satisfied. That's true for every single problem. Both of these 2 rules should be satisfied. Okay, here's what you're going to need to do for today in the homework. First thing you're going to need to know is polar. Polar means unequal, unequal sharing of electrons. And nonpolar means equal, an equal sharing of electrons. Now, if you were taking an honors or an AP course, what we would have you do is we'd have you look at electronegativity values, and we'd have you calculate, kind of subtracting 2 electronegativity values to see if it had a certain number range, so that would make it polar or nonpolar or even ionic. For the purposes of our class here, guys, here's what we're going to do. We're going to say that if they're different atoms, like if you have an H bonded to an F, a hydrogen bonded to a fluorine, that's polar. There's unequal sharing of those electrons there because the 2 atoms are different. Nonpolar, on the other hand, is saying if you have an H, a hydrogen, bonded to another hydrogen, another H, that's nonpolar. So different atoms versus same atoms, that's what we want you guys to do in practice, but then know that the definitions are based on how those electrons are being shared. So in a bond, if they're the same atoms, they're sharing them the exact same way. If they're different atoms, one atom is going to maybe pull to those electrons a little bit tighter than the other one might. You can also look at polarity and nonpolarity in a compound. So you'll see down below here, the fact that I have bromines and hydrogens around this carbon makes this atom polar, or sorry, this molecule polar, versus this guy that has a C and then 4 H's around it. That would be nonpolar, just because it's the same atom around it. So even though it's an unequal sharing of electrons, everything's being pulled equally each way, up, down, and side to side. Great. So that's polarity versus nonpolarity. In practice, the questions that we'll ask you is very similar. We'll have you look at bonds, and then you'll have to say, is it the same? Yes, it's the same. Perfect. Nonpolar. Is it different? No, it's not different. Nonpolar again. I always confuse these 2, by the way. I see polar and I think equal, but polar is unequal. And then I see that word non-polar and I think, oh, non-polar must mean unequal, but it's actually the opposite. Non-polar means equal. So think polar, like on the Earth, means you're like have 2 opposites, or polar as in a magnet means you've got like a north and a south end. So polar means unequal, So then if you're not unequal, you're equal, if that makes sense. It's kind of like a double negative in that case. Great. We'll skip those 3 slides. They're not super important. Okay, so here's just a picture of what we're talking about. Here is a non-polar example. You'll see that the 2 atoms, the electron clouds there are evenly distributed, versus over here, the bond, these 2 atoms must be different because this one atom looks like it's bigger and it looks like it's pulling some of the electrons kind of towards it. Some of that electron cloud distribution is more focused on one atom than it is on the other. And then below here, you'll see that I've got a polar bear. That's where on the scale of polar to non-polar, that's where it would be. And then on the left over here, you'll notice that I have a non-polar bear. I think that's funny. All right, guys, that's it for today. Thank you for paying attention. Have a great rest of your day. We'll see you next time.